Hello, welcome to the presentation of our paper. For the future 3D point cloud semantic segmentation task, the model receives support point cloud with annotations about the novel classes like table and the query point clouds. By leveraging the knowledge from annotated support samples, the model needs to segment the query into these classes. We revisit this task and highlight two significant issues in the current FS-PCS setting. The first issue is foreground leakage. The 3D segmentation practice fits model with sampled points from the scene, but the current sampling process in FS-PCS is non-uniform, favoring more points in the foreground than in the background. This leads to foreground leakage, a noticeable density bias toward foreground classes. As depicted here, the inputs in the third and fifth columns are from the corrected uniform sampling and show balanced point distributions, while the input in the fourth and sixth columns using biased sampling exhibit denser distributions in the foreground door or board than in the background. This leakage allows previous models to exploit density disparities for easier segmentation instead of learning semantic knowledge transfer from support to query. Consequently, this issue renders the current benchmark unable to reflect the true pure-shot performance. Addressing this issue by changing biased sampling in the red box to uniform sampling in the green box unveils a significant performance drop in the existing methods. It underscores that the previous methods largely rely on the density differences exposed by foreground leakage to achieve seemingly superior performance, highlighting the imperative need for correction. The second issue is sparse point distribution. The current FS-PCS input is constrained to only 2048 points during training and inference. However, this sparse input severely limits semantic clarity, making it difficult to distinguish objects. As shown here, it's even challenging for humans to distinguish the door and the surrounding wall in the 2048 point input in the first row. The same applies to the second row to discern board from other classes like window. These sparsely populated, semantically limited inputs introduce significant ambiguities, hindering the model's capacity to exploit semantics. To address these issues, we propose a standardized FS-PCS setting where we increase the number of input points tenfold to 20,480 and eliminate the foreground leakage through uniform sampling. It provides clearer scene representations and uniform distributions, aligning the task more closely with real-world scenarios. We further introduce a novel model named COSeg. Existing models are based on feature optimization, refining query or support features and passing these adapted features to non-parametric modules for predictions, implicitly modeling correlations. However, instead of operating on features, we propose correlation optimization, which directly uses correlations as input to learnable modules, enabling explicit refinement of correlations. In COSeg, we compute the correlations named CMC for each query point, representing its connections to all category prototypes. Then the correlation will be the input to the following HCA modules. The HCA module leverages two underlying relationships to refine correlations. First, the query points are all related. Their correlations to all prototypes are also connected, leading to point-point relations corresponding to the first half of the HCA module. Second, classifying a single point depends on its relative correlations to foreground or background prototypes, forming foreground-background relations corresponding to the second half of the HCA module. Moreover, few-shot models undergo training on base classes and are evaluated on novel classes. Then these models are inherently susceptible to familiar base classes within the test scenes, hindering the accurate segmentation of novel classes. To address it, we propose learning prototypes for the base classes in a non-parametric manner. When segmenting the novel classes, a query point corresponding to the base classes should be considered as background. Therefore, leveraging base prototypes, we introduce the BPC module to calibrate correlations for background within HCE, mitigating potential interference from base susceptibility. Our experiments establish the new benchmark under the corrected setting and demonstrate a significant performance advantage of COSeg, setting new state-of-the-art records. The visualization clearly shows better segmentation results achieved by COSeg. We also present extensive application studies showcasing the superiority of correlation optimization and offering further insights into our designs. In conclusion, we identify two critical issues in FS-PCS setting which has undermined the validity of previous progress, and we introduce a standardized setting along with a new benchmark. Moreover, we propose a novel correlation optimization paradigm for better few-shot generalization, and our model incorporates HCA for effective contextual learning and BPC for background adjustment. We hope that our work serves as a foundation for FS-PCS and sheds light on future research.